The electric motor in the racing car can also be used as a generator to charge a battery pack. It's known as a motor generator unit, MGU. The rotating wheel of the car causes the magnet in the MGU to spin near a coil of wire. This induces a current in the coil when the coil is connected to the battery pack. Name the energy store of the battery pack that increases when the battery pack is being charged. Remember, the energy store that increases at this point is chemical energy store. Explain why the kinetic energy store of the car must decrease when MGU charges the battery. Something that we need to highlight here is that as charging is taking place, we need to remember the law of conservation of energy. Energy is neither destroyed, but is converted from one form to another. So in this case, kinetic energy of the car is transferred to kinetic energy, or rather to chemical energy of the battery pack. So in that way, the kinetic energy will slow down, will decrease in a sense that is converted to the chemical energy form. And this is according to the law of conservation of energy. So we're supposed to explain why the kinetic energy store of the car must decrease when the MGU charges the battery. So we're going to say this is because kinetic energy of the car, this is because the kinetic energy of the car is transferred to chemical energy store of the battery pack. And this is according to the law of conservation of energy, that energy cannot be destroyed but can be converted from one form to another. Moving to the next question, we are told that this question is about magnetic field. The student positions a thick wire vertically through the center of the horizontal card. The student then passes a constant current through the wire in the downward direction as shown on the diagram, as shown on the diagram. And then we're supposed to say, let's check what question we are asked. We are told in the diagram above, in this diagram, we're supposed to draw the pattern of magnetic field produced due to the flow of current. Actually, this is going to form concentric magnetic fields, which are circular around the conductor, and we can be able to predict the direction of this field using right hand grip rule. So the field will be pointing in that particular direction. Another question we are supposed to answer in this section. Let's check. Yeah, so this is the direction in which the field will be pointing. When you use right hand grip rule, you hold that wire in such a way that the thumb points to the direction where the current is going, and the other fingers that are running around the conductor will be pointing to the direction of the fields. So I think that is now clear according to the diagram. Now we need to move further down so that we can be able to look at other questions that are asked here. We are told describe the method the student could use to show the shape of the magnetic field produced by the current in the wire. In this particular question here, the student supposed to sprinkle iron filings, on the cardboard. And once the student has sprinkled those iron filings on the cardboard, is to turn on the flow of current, should switch on the current to flow through the wire. Now once he has done that, the student should tap gently the cardboard so that the iron filings are going to rearrange themselves to form a particular pattern that is shown on the diagram above. So if we assume these are just iron filings, if the student sprinkle iron filings and then tap this cardboard, these iron filings are going to rearrange themselves in that particular order. So once we have obtained the iron filings, we need also the pattern of the iron filings. We need also to mention how do we determine the direction of the fields. Then at this point, the student should use a compass, a plotting compass, in order to determine the direction of the field. And after writing all this, now this is now a full description on how the student could use to show the shape of magnetic field using a round produced by the current uh, flowing through a straight wire like that. So we need to move down. The student then removes the card and sets up the second wire next to the first wire as shown there. So since we are having current flowing in the same direction through the two wires, it means there are going to be magnetic fields around the two wires which are going to interact. Now, the moment these magnetic fields interact, they are going to attract each other. And in that way, you are going to experience an attractive force there. So how are we supposed to respond to this particular question? Then we are going to say, since both wires have a current, then magnetic fields are going to be created around each of the wires. Then when the two fields interact, a force is created according to Fleming's left-hand rule, and then the force is going to be acting towards each other. So if you consider one wire, that wire is going to be attracted to the other. So there is an attractive force that is acting there. Some other times you may be asked to state, how can the force increased? How can the force increased? In this case, the force can be increased by increasing the amount of current that is flowing through the wire. Also, the force can be increased by using thick wires, which means that more current can be able to flow through the wire, since when you have a thick wire, there is low resistance, so more current can be able to flow. In that way, that's going to increase the amount of force. Moving to question 3, which is talking about the national grid system, and we are told a national grid is used the national grid is used in the United Kingdom for the large-scale transmission of electricity. The photograph shows solar panels connected to the national grid. The solar panels provide direct current to a device that outputs an alternating current, so that the energy from the solar panel can be supplied to the national grid. So we're supposed to explain why a step-up transformer is used to supply the national grid. In the first place, you need to understand what we mean by the term step-up transformer. So before I mention what we mean by step-up transformer, let me say that in the national grid, remember, electricity is transmitted from the power plant, from the generation, the plant of generation of electricity, to very distant towns where it's being used, or where the consumer makes use of the electricity. So since this electricity is going to be transmitted through cables, then it has to be transmitted at a low current, so that it can be able to reduce power loss through heating processes. So the step-up transformer step up voltage. It increases voltage, and in the process, current decreases, so that uh, electricity is transmitted at high voltage but low current. So explain why step-up transformer is used. So a step-up transformer reduces current and also increases voltage. In that way, it's going to reduce the heating effect in the wire in the process of power transmission. It reduces, a step-up transformer reduces, let me write now, it reduces current, and this reduces the heating effect in the process of power transmission. This is the label of a step-up transformer. You can see now we have the input voltage, which is 15,000 volts. Output voltage is 34,000 volts. Then from here, you can see that a step-up transformer increases voltage. A step-up transformer increases voltage, and we can be able to see that in the number of turn ratios between the secondary coil and the primary coil. When you want to differentiate between a step-up transformer and a step-down transformer, you need to look at the number of turns in the primary coil and the number of turns in the secondary coil. So a step-up transformer has more turns in the secondary coil than in the primary coil, so that more voltage is going to be used. So state the formula linking input voltage, output voltage, and the turn ratios of a transformer. And at this particular point, we're going to highlight this and say number of turns in the primary coil over number of turns in the secondary coil should be equal voltage in the primary coil over voltage in the secondary coil, which we can be able to highlight. And then we are going to calculate the number of turns in the secondary coil, so we can be able to substitute whatever we have in this particular question, and we try to make number of turns in the secondary coil the subject of the formula, which is going to give us 1400 times 340,000 times 340,000 divided by 150, that is 15,000. And if we simplify this, we're going to get 31,733 31,733 tons. A solar panels produces constant direct current. Explain why a transformer will not work when connected to constant direct current. Remember, when direct current flows through the primary coil, what happens that it flows in one direction. So the kind of magnetic field is going to create constant magnetic fields which do not change direction. So we are going to say here that this direct current gives constant magnetic fields. DC current, direct current, that is, gives, let us right, direct current gives constant magnetic fields which do not change direction. And for induction to take place, the transformer requires magnetic fields which are constantly changing direction. So that is the reason as to why a transformer will not work when connected to direct current. A mobile charger X contains a transformer and is used to charge a phone's battery. Diagram 1 shows the information on charger X. If you look at this information that we are provided here, input voltage is 230, output voltage is 5 volts. So meaning this is a step down transformer. Output current is 1.2. The power of the charger can be calculated using the formula power equals to current times voltage. Work out the output power of the charger. So to work out output power of the charger, we're going to use output voltage times output current. So that's going to be 1.2 amperes times 5.0. So this is going to be 6.0 watts. If we work it out, we're going to use this and also we're going to use 5, and this is going to be 6.0 watts, which we can now transfer this point. Calculate the input current to the charger X. Assume that the charger is 100% efficient. So it means that if it's 100% efficient, it means input power equals to output power. So we can be able to write here and say power in, if it's 100% efficient, power in equals to power out, and the power in is actually input current times input voltage, and the power out is output current times output voltage. So in order to get input current, it's going to be the power that we had gotten in the previous question, which is 6.0, divided by the input voltage, which is actually 230. So we can be able to say our answer is 0.026 amperes as the input current. Charge is given by the formula. Charge is given by formula current times time. And in order to find time is charge over current, so we can be able to substitute 10,500 divided by 1.2, and this is going to give us what? 8750 seconds, which we can be able to convert to minutes, because in this question we were given the current 1.2, so we can be able to use it there. So if you work out the value here, we are going to get 8750 seconds, which we can convert to, this is now in minutes. We have to give it in minutes because of the way the answer was expected, as expecting us to give it out. So we can divide by 60, and then we're going to get 146 minutes as the time taken. Charger Y can also be used to charge the mobile phone battery, and diagram 2 shows the information label for charger Y. The input voltage is 230, the same way it was in the other part in X. Output voltage is 5, but output current is 2.1. Explain how the time taken to transfer the same amount of charge to the mobile phone battery will be affected when the charger Y is used to instead of charger X. You see the output current for charger Y is 2.1, which means it's giving more current out. So explain how the time taken to transfer. In this case, we are going to see, since it's giving out more current to charge, it means time is going to decrease. So we are going to say it's going to take a shorter time to charge that particular battery. So time will be less because current is greater, so it charges faster. So it charges faster. You see the current small, so it charges faster. Let's move to part C. Both chargers contain step-down transformers. Explain how a step-down transformer works. You may include a diagram to support your answer. This diagram usually don't have marks, but usually when you draw them, actually they can enable you to explain your answer quite effectively, because you can say refer to the diagram. So we are having the primary coil here, the primary coil, and here we have the secondary coil. Now if you look at the number of turns in the secondary coil are actually less. This is the output, so this is where we have the secondary coil, they are less, but in the input we have more coils. So when current, let us try to identify when AC current flows through the primary coil. When AC current, let's be specific, when AC current flows through the primary coil, this is where we have the primary coil, a magnetic field that is constantly changing direction, a magnetic field that is constantly changing direction is created. When this magnetic field that is constantly changing direction is created, it cuts through the secondary coil. It cuts through the secondary coil, inducing a voltage in the secondary coil, resulting to a flow of current in the secondary coil. Yeah, this is the secondary coil that we are talking about. So which means that when there is a voltage in the secondary coil, since in the conductor that is used to make that secondary coil has electrons, then the electrons now will be provided with electromotive force. Yeah, since we have yeah, since there are fewer turns in the secondary coil, which means that less voltage is going to be induced in the secondary coil, thus reducing the voltage. Now since we be having a voltage now in the secondary coil, what will happen is that electrons in the conductor are going to have energy and they will start moving. So in that way, current is going to flow. Right, let's move to the next question so that we can see what is expected in question 5. In question 5, a transformer is used to charge a mobile phone. The diagram shows a label of the transformer. Output current is 0.067, output voltage is 5 volts, output current is 3.1. And when you look at this is a step down transformer because the output voltage is less than the input voltage. Yeah, so to check which type of transformer, that's actually what you need to look at. Explain how the information in the label shows that the transformer is a step down transformer. We are going to say output voltage is actually less than the input voltage, because if you look at that information, we can be able to attest that this is a step down transformer. State the formula linking input voltage, output voltage, and turn ratio of a transformer. We've mentioned this before, so let us try to highlight that. Yeah, so before we move to that, we were to show that the transformer is 100% efficient. To show that it's 100% efficient, you need actually to confirm if power in is equal to power out. Input power equals to power output. Then you are going to use the information provided in order to work out that. So if we work out this particular part using power in, we're going to say 230 times 0.067. If you multiply that, should be equal to 5.0 times 3.1. So if you try to work out this, let me try to reduce this size. Then if you work out the left hand side, you are going to get your answers 15.41, 15.41, yes. And the other side, it should be 15.5, which is actually approximately the same. Then from here, we can be able to say that uh, the transformer is 100% efficient approximately. State the formula linking input voltage, output voltage, and the turn ratio. So in this way, we can be able to write. Actually, we've answered this. We have answered this before. Let us just put it down so that we can be able to go straight ahead and work out the next question. To calculate the number of turns in the secondary coil, you are going to substitute the information provided into the question that we have written in Roman 1 of C. Is the information, so that we can be able to make number of turns in the secondary coil subject to the formula. And if you work out this, we're going to get 32.6, which is approximately 32.6, which is approximately 33 turns in the secondary coil. All right, moving further to question number 6. Question number 6. There is a step up transformer at the power station at the end of transmission line, and a step down transformer at a distant. Right, okay, let's go back to the question. There is a step up transformer in the power station end of a transmission line and a step down transformer at a distant town. Explain why step up transformers and step down transformers are used in this way. Remember, at the power station, voltage is supposed to be stepped up so that it can be transmitted through the cables to distant places. But near the town, that voltage has to be stepped down. The voltage has to be reduced so that it can be safe for the consumers to make use of them. So in that way, we are going to highlight those aspects and say at the power station, a step up transformer is used to increase the voltage so that electricity can be transmitted at high voltage and and also at low current. Can be transmitted at high voltage and at low current, so that to minimize power loss in the process of transmission. Next, there is a step down transformer near the town to reduce the voltage. There is a step down transformer near the town to reduce the voltage so that the consumers can be able to use it and for safety purposes. And also this is for safety purposes because if people will be using electricity at high voltage, there are chances of getting electric shock. State the formula linking input voltage, output voltage, and turn ratio of the transformer. Actually, in this video, we have really done a lot of questions which are having the same question. So I'll rather consider you try those questions so that you can be able to see if you are able to answer them. Now, pause the video, try to work them out, and then check if this is what you got. So I believe you've attempted them, so we can be able to write the formula we expected. Then if we substitute, we can say that is 15 kilovolts divided by 340 kilovolts should be equal to 3,300 over number of secondary turns. So that if we try to make NS the subject of the formula, we can be able to get this rearranged to, and if you work out this, you're going to get 74,800 tons. 74,800 tons. Okay. All right, let's move straight to where we had left. All right, so we are done up to that point. Okay, if you rearrange the formula, you're going to get 74,800 tons. In part C, transformers in the national grid have efficiencies less than 100%. Suggest which energy store of the transformer increases as a result of the efficiency being less than 100%. Actually, there is a heating effect, so we can say thermal energy store increases, and that reduces the efficiency of a transformer. The iron core of a transformer is an electric conductor. When the transformer is in use, the primary coil causes a changing magnetic field in the iron core, and this causes a small current to be induced in the core. Explain how current is induced in the core of the transformer. So what we need to understand is that when current flows through a primary coil, magnetic fields are created which are constantly changing direction. Now, as the magnetic field keep on fluctuating, increasing and decreasing, those fields cut through the secondary coil, and in the process a voltage is induced in the secondary coil, which results to the uh, provision of electromotive force for the electrons in the secondary coil to start flowing. So since there is a voltage now that is induced in the secondary coil, that voltage makes the electrons to gain electromotive force, they start to flow. Due to the flow of electrons, then there is now a current that is registered to flow in the secondary coil. So we can be able to say in this particular question that when the fields cut through the secondary coil, let us try to write this. When the fields cut through the secondary coil, a voltage is induced in the secondary coil. Yeah. The next point we can say, since there is free electrons in the coil, since there are free electrons in the secondary coil, they are provided with electromotive force to move around, and this results to the flow of current in the secondary coil. And this brings us to the end of this particular video. If you have found value on how to answer a particular question, especially to do with electromagnetism, consider subscribing, and also you can be able to share this particular video to all your friends. Thank you for watching, and also watch out for more that is coming up.